So hi, welcome everyone to this OpenGeoHub Summer School edition 2025. This is a tutorial by me. I'm Edzer Pebesma. I will talk about raster and vector data cubes in R and Python. Usually we are teachers in the summer school are asked, 6 months before the event, like, what are you going to teach? Right? And then I always go like, oh, it's 6 months from now. So what would I like to be able to teach in 6 months from now, but cannot teach right now, right? So to make life a little bit, you can also pick something off the shelf, right? But this is not. So this morning was a complete surprise. Until yesterday early, what would come out. But this today is also of interest. Yeah, I made some progress. So I'm, as you know, probably most of you might know, I did a lot of work in R, and extremely little in work in Python. You can also see that as authors, I declared here, this is me, but this is also GitHub Copilot, and with some help from Claude. I actually followed the tutorials. So a lot of people in R use RStudio as their IDE. Who of you uses RStudio for R? Yeah. So who of you uses Positron? Yeah, there are some people do. Who of you uses Visual Code or so? Right, quite a few. So there's this thing called Positron, which Posit, the company that formerly known as RStudio, that now sort of tries to make its way into the data science market. So no longer just focusing on R, but equally focusing on Python and on other data science things like Databricks and so on. They developed this thing called Positron. It's here. I can open it. I hope this will work. Right, it's a little bit colorful and so on. Well, I had to enlarge the fonts from Tom. It looks better if I don't. But anyway, so it is so as you might know, Visual VS Code is not an open source platform. It's something from Microsoft, but it's built on some kind of open source kernel, OSS it's called, or whatever it is. And Posit took that kernel and built on top of that an IDE. So again, the Visual Studio type thing that you can use to develop notebooks, right? So that's what we are looking at now, notebooks. And so this is let's say a multimodal or multi-language notebook, yes, and that is sort of classically something complicated. We all know about Jupyter Lab, and so who has used Jupyter? A few, yeah. So more than half. And as you know, you can use Jupyter for Julia, or for Python, or for R, but with emphasis on or. You cannot mix R and Python code in a Jupyter notebook, right? So that will get you into trouble. So there is something that could be done with RStudio. We have been working on this and so on, but apparently with Positron, this works better in the sense that RStudio, for instance, if your R process crashes, then whole RStudio crashes with it, so to speak, and you need to sort of work around it, and this can work better with a set of kernels, as you can see here on the right, an R and a Python kernel that you can switch between. Here's the R and here's the Python, although it doesn't really look like it. But yeah, here's the Python, and here's the R. Right. It messed up things, but anyway. So I pointed you, if you are following, if you were preparing this case, in the unlikely case that you prepared for this tutorial, I pointed you, I think, to the GitHub site where everything is, and that is here, OGH25. So on github.com/Edzer/OGH25 is the repository where everything that I do today, this afternoon, is. There is link to the slides of this morning, link to the tutorial workbook, which is again here, and as you can see, there is this RVDC, raster vector data cubes .qmd file. So that is a Quarto markdown file. It has a markdown file. I think it might be identical to an R markdown file. I forgot, but now on the Quarto. Quarto is another product of POSIT, which is basically a processor for markdown files that where you can create books. Yeah, for instance, here is this this book on which was mentioned before, the book on spatial data science with applications in R is completely online. It's created with Quarto. So Quarto can use the source code of this, which is also online, and create a PDF, right? And I sent a PDF to the printer, and the printer prints the PDF, and you have your hard copy. And can also create an HTML thing with all the things, all the bells and whistles, like tables and contents and links, and there's all these kinds of things like like code sections that can be folded in and out, and also this new thing with the tabs, right? So there is a way to do a certain thing here with R and create a plot, and you see the code. There's a way to do it with Python, and there's the code, and that also creates a plot, slightly different plot. We're not yet done with this whole affair, but as you can see, so we are now in the process, or mostly I and people I work with, but it's hard to move Roger into writing Python code. But anyway, that's not so hard. It's not fair to say. But so we are basically in the process of translating all the R, if you want, translating all the R sections to Python code, so that what we do in R, you can also do in Python, and that you see it like one by one in the same thing. Yeah, so that's a slightly different setup from what, for instance, the GeoComp X people do. I don't know if they are .org. The geocomputation people, amongst them Martin Pronk, who's there, who's working on the Julia book, they work on different books. So there's one with R, there's one with Python, and one with Julia, and they are different books. So they might have the similar setup, but there's no, let's say, text sections and then code, like this code does exactly that thing. And so there's not this one-to-one correspondence, and it's pretty hard to do one-to-one correspondences, by the way. So I think I just had a crazy idea and make my own life terribly complicated. But that is sort of, one of the things you're allowed to do in academia. Yes, that is just, make your own life as complicated as you want. Anyway, I also don't have a deadline for this. But this was a deadline, right? So I made myself into doing this, and now we have 1.5 hours, and I started 10 minutes with the introduction. So there is quite a markdown file which is here. So you can, if you want to, you can clone this repository and work from there and use a quite a markdown file. You should be able to open it with RStudio. Alternatively, you can open it with Positron, or you can compile it with Quarto. Yeah, the way you compile that is with this. For instance, I could say, so I'm here. Let me just pick a. So I'm here, and then I say, well, I have a make file, and the default target is just to render it. It's just Quarto render with the Quarto markdown file. I render it, and and it's being rendered, and that means that the HTML is being created, and the HTML is nicer to look at. Except just that you cannot run it there, and the HTML is here, right? This is the GitHub Pages site that is created here. So this is the output of the rendering, and this is basically the human readable but the non-executable form. There is non-executable. I'd say that there is actually an interesting development. Who of you has worked with? What is it called? Is it called WebR or so? This WebAssembly version of R? No. Nobody. Well, there is this thing. I think Python also has that you can run Python, you can run R in the browser, and you can also sort of instrument these notebook such that you, in the HTML, you don't just see the code, but that you can also run the code. That you get with every code section, you get a run button, and you can click on run, and it runs, and you see the output in the HTML. So that means you have a web assembly version of R and all the packages that come with R, which is quite nice. Because then you can change things in the HTML. You don't have to set up anything like RStudio or Positron or whatever you're using, right? So you just need a browser. You can do these things on your phone. But that is besides the point that I want to make here. So I want to talk about raster and vector data cubes in R and Python. Because I think they are of interest as an interesting data structure that are not, well, that we run into often, and for which Python and R have pretty strong infrastructure that I will try to demonstrate today. But first of all, we will look at what an array is, and as I said, I used to GitHub Copilot quite a lot, and it was extremely good in doing the whole section on arrays and examples and stuff on. And then I went into spatial data, and then raster data cubes. It was pretty good. And I went vector data cubes, and it completely messed up, right? It was just nothing working and absolutely nonsense. It had no idea. And it was fully hallucinating. So this is clearly the vector data cubes is something that is relatively obscure. It's not completely covered by large language model at the moment. Arrays are basically data structures. Yeah, arrays are data structures that can hold multiple values in more than 2 dimensions, 2 or more dimensional, 1 dimension. But if you have a 1-dimensional array, you basically have a vector, right? And if you have a 2-dimensional array, we typically call it a matrix. Yeah. Why would you call it an array? But array is the generic term for multi-dimensional structures where dimensions can be 1, 2, 3, 4, 5, and higher, and so on. So they are multi-dimensional structures of elements, and the elements in an array have to be of a single type, right? And typically they are numbers, yeah. But numbers could be integers, could be floats, but we don't care about that today. But they could also hold other things. They could also hold strings, yes, or they could hold logical variables, Boolean variables. Or they could hold. They could even hold dates, right? If you want to do that in ARIA or factors, you have to hack things a little bit around, but it can be done. They could even hold, you can even have an array of, and you can have a list that's an array. Yeah, so you have basically, you have an array, and the type is list. So every array element is a list element, and list elements can be arbitrary, right? So you could put anything in it. To question to what extent it was useful, but we found out at some stage that work that actually Lorena Abad, who regrettably died earlier this year, came in accident, but she was exploring the concept where you have arrays and the content of the array elements are geometries. She was looking at temporal changes of geometries, like the extent of lakes or the extent of mud flows or the extent of glaciers and these kinds of things, how they change over time. So you would have the item as a row, and in the columns you would have the time points, for instance. So that is, but we will first look at arrays. Here we do this in R. I will go to the in a while to the Python elements. So in R, it is just as simple as you create a sequence. Yeah, the sequence is of class integer, which doesn't have a dimension, right? But once we set the dimension to 6 and 4, there are 24 elements, so we can do that. The product of 6 and 4 is 24. We see that it has a dim attribute, and we can ask the dim attribute, and we see that the class of V has suddenly changed. Although there's no class attribute, this is automatic. This is sort of the automatic classing of array type, vector type objects, which are sort of the basic data types of R. And we see that it's an array and subclass is matrix because it's 2-dimensional. And we can then print it, and then we see that it's printed as a nice table, right, which has 6 rows and which has 4 columns. Yeah, so we have rows and columns in that order, right? So the numbers 1 to 24 have been arranged column-wise. Yeah, so they have been spread over the columns of this matrix. That is not a given. You could also put it row-wise, right? You could have done that. I could have done it. I can create it with, if I use the function matrix and I say use the numbers 1 to 24 and don't do it the default way, but do it by row. So if I specify by row is true, I get it filled row-wise, right? The numbers 1 to 24 are distributed in that order over the rows. And that's of course a different thing. So that matters. The reason why it's column-wise is that the storage order of R uses what they call column major matrices. Yeah, so you first fill the columns and then the rows. There's like, you know, programming languages like Fortran and C. They also have these things. Like I think that Fortran is column major and C row major, or the vice versa, or something like this. These sort of the details of programming languages, right? So you have to do one thing and be unambiguous about that. You can see here that if I transpose this matrix, so here I set the dimensions to 4 and 6, and then of course I still have a column-wise fill-in, yeah. And then I transpose the matrix that I also get this thing, right? So I had a 4 by 6, and that now becomes a 6 by 4 matrix where the filling is by row. So you can do that by transposing matrices. Yeah, there's many operations you can do with matrices, like all the matrix algebra, and so all the linear algebra is all there, right? It's all in R. R is language focusing on data analysis, so it has these facilities, right? Python is a generic programming language, so you need to load a package called NumPy to do linear algebra, to do arrays, matrices, and linear algebra, so which is fine because many people do, right? It's pretty simple. If you then sort of look at sort of how are the elements ordered, you see that in V this is 1, 2, 3, 4, 5. It's 24. It's of course this, but for V2, which is this one, you see that the elements are ordered column-wise, right? So if I say, give me the vector representation of this thing, it basically gives me the column-wise representation because that's how the elements are stored in memory, right? That is the sort of the order in memory. There's the number 1 there, and there's the number 5, and there's the number 9, and so on, right? And 13 that you can see here, that is the order in which. So arrays are basically, you know, elements in continuous memory. Yeah, they are vectors that where the machinery keeps track on how is it split up in rows and columns, or even more dimensions. Yeah, but they are continuous kind of memory spaces in what they do. So we could do, for instance, higher dimensions. We can, of course, distribute the numbers 1 to 24 over something that has 2 rows, 3 columns, and then 4. Well, whatever it is, sort of think of it as layers, right? If in the flat we have the rows and the columns, and then we go in the altitude, we go, or in the depth, we go with the 4th element. So we get now 4 sort of submatrices that are all printed here, and here is the sort of the index of the third dimension, 1, 2, 3, 4, and we see that it's basically filled again column-wise, 1, 2, 3, 4, 5, 6, 7, and so on. So we can do that. And we can also select a certain element 2, 2, 2, and that means that is the second layer, and then the second row and the second column, that is this element, right? So we select a single element with 3 indexes from that array, and we get that array. So you can get that array out of. Small difference between Python and R is, of course, that if I say the second row, that in R that has the index number 2. In Python, the second row has index number 1, because indexes are 0 based. So they're counting 0, 1. Yeah, the second number is 1, 0 based. Yeah, which has a reason. I'll come to that. Here is a Python section where we can do the same thing. So we say import numpy as np. So numpy, that is the package that you need. Otherwise, you don't have arrays in Python. And then you say np.arrange. np is then basically, the short for numpy. We could also say import numpy and then numpy.array and so on. Arrange the numbers 1 to 25. Yeah. So this is the range, and then reshape that into this, with this shape. And then interestingly, we had shape 2, 3, 4, which gave us 4 layers of 2 by 3 matrices. Now we get, let's say, 2 layers of 3 by 4 matrices. Yeah. So that is what NumPy does. Yeah. So this is not so surprising. It just means that the order of dimensions is the other way around, right? So it's the 2 is, let's say, the last index, the 3 the middle, and the 4 the first. When the first is the column, at least. We can then also get element 1, 1, 1 out of this. That means the second one, that means the second layer, yeah, the second column, I think, and the second row. So that is this element that we get out. Yeah, element 18, which is different from the element 10, which we had here, the 2, 2, 2. And we had a 10. So we try to move this and say, okay, we can then do it the other way around. So reshape A. So A is again a vector. I can reshape it as long as the product of these numbers is equal to the length of that vector. It will create it will fit, so to say, the shape. If I would say 4, 3, 3, it would basically give an error and say, no, I can't do that. I hope. And this gives us something with 4 layers, but every layer has 3 rows and 2 columns. And you can also see that the distribution of the numbers is row-wise, right? So they're not go here 1, 2, 3. They go 1, 2, 3, 4, right? So this is sort of a row major storage. Yeah, the one element, next element is in the same row if there's place in that row, and not in the same column as R does. So we have a somewhat different memory layout, but in principle we can do exactly the same things, right? We just have to going from one to the other, we need to rethink order of dimensions and also row major, column major. And then we get number 1, 1, 1, which is the first, which is the second layer. There we go. The second column, 1, and the second row, which is then number 10, right? So I get a 10 out. So you could then do these things, and you can do all kind of operations in it. What basically happens is, if I want to find an element, if, for instance, I want to find element 2, 3, row 2 and column 3, and I have 6 rows, then my index, sort of the place where I have to look in this array, the index is computed as the column index minus 1 times the number of rows plus the row index. Yeah, so because I have to, I'm jumping the number of columns. Yeah? So this is, first column, second column, third column, and so on. So I have to go the number of columns times the length of a column, which is the number of rows. Yeah, to find that index, and that index is then 14, right? So if I just ask for element 14 in this matrix, I get number 14. If I do row and col 2 and 3, I get number 10. That was not what I expected. So, but column 3, row 2 should be 14. Yeah, so there is an. I probably this is because I changed phi here. Yeah, so sorry about that mistake. If the phi is my original phi, then I get a 14 out here. Yeah. I messed up my phi. So, right. So, and that idea extends to higher dimensions. Yeah. So arbitrary dimensions. So if you have something that has dimensions 2 times 3 times 4, and you're looking for element 2, 2, 2, then the index, the place in that vector is k minus 1 times the number of rows times the number of columns plus j minus 1 times the number of rows plus I, right? Which is just an index where you can find, oh, in this vector, where do I have to look for, where do I find element 2, 2, 2? And that finds number 10 here, right? And that is, let's say, exactly the sort of the powerful thing of arrays, that whatever the dimensionality is of my array, if I have a 10-dimensional array, if I want to find an element in that array, it's just sort of, it's a single index in a vector that I have to sort of find, that I can find by a very simple mathematical, a very cheap mathematical operation. Yeah? So it is easy. In my high-dimensional arrays, I know where elements are, right? There is no searching going on. There is no lookup going on, and so on. Irrespective of how complex it is, of course, this expression becomes longer, but it's a very cheap expression. So it is in that sense a very powerful data structure where, as complicated as it might get, you always know where elements are, right? You can always find elements in a very cheap fashion. I have the same thing here for Python. It looks similar. And then, of course, my element is 1, 1, 1, because this is zero-based, the second row, second column, second layer, and then my index is computed like this. And now you can see that, oh, okay, and something went wrong because no, the index is 9, which is, of course, the 10th element, right? And then I ask for the 10th element, and I get this value, this value 10. Or I do A111 also gives me this 10 value, right? So it's the same thing I can do in Python or in R. You see that now. You could argue, well, this is also exactly why Python has zero-based indexing, because this expression is much simpler than this expression, because we don't have the minus ones, right? We can drop this minus ones in that expression in Python. Right, so that is actually the reason why this comes from the C realm, where you have pointers, and sort of the first element is sort of, you don't shift the pointer. For the second element, you have to shift the pointer with one position to the second element, right? So you add the pointer, you move the pointer one element. It is kind of what's behind this. Yeah, so this is getting a little bit nerdy, but forget about it. Yeah. So finding an element in a 40 array, you could do that. Finding elements in arrays comes at a near zero cost. Yeah, it's just an arithmetic operation. It's cheap. You know where things are. Finding elements in data frames or lists is more complex, because it may require through names, right? You often work with column names and so on in the data frame. So you have to match the name, and then you find the column in the data frame. Data frames, at least in R, are lists of equally sized vectors. So you find then the right column, and then you have to search in that column. So it's a two-step search, a two-step index, two-step search, right? Whereas arrays is always a one-step search, irrespective of the dimensionality of this thing. It's one step and cheap. So you cannot reduce in a data frame. You cannot reduce rows and columns to a single index. Yeah, then comes the question: are data frames also arrays? In general, they're not. They are vectors. They are lists of vectors of equal length, and the vectors are not necessarily of equal type. Yeah, that is the strength of a data frame. You can have one column that's numeric, and one column that is character, right? That's names or so, and one column that is dates with a birth date of people or something like that. It can all have that, sort of maintain that, right? And the idea is that this, the same index for all these vectors is the record, right? The records, of course, don't exist, right? Because R and pandas, in pandas, those data frames in Python, pandas and so on don't think of records, right? They're not collections of records like relational databases have records and collections of records. They have collections of columns, right? And so if they are heterogeneous, then you cannot see them as matrix because they are of different type. And of course, you can try then to convert them into matrices, and then R will do its best, right? It will not error, but what you get is basically It looks for a common, something that where everything can store it into. So in the worst case, that's character. So in this case, it's going to convert everything first to character, because that is a type where everything can be put into, and then you get this character matrix, which you could transpose, but which is relatively useless, because of course this is like a number as a string, and then a label as a string, and then the data as a string, right? So it makes life more complicated than it already was, right? Here you see a data frame with numbers, and a logical, and that will, if you convert it into a matrix, then you see that the logical will be converted into a numeric, right? Doesn't have to convert everything into character, because because logicals are 0 or 1 or NA. And logicals in R, Boolean variables can have 3 values. Yes, true, false, or NA, right? It's a clever thing, useful, very useful. I think the lack of NAs in Python is really the biggest thing, between the biggest sort of thing between the two languages. Yeah, so Python doesn't have missing values, doesn't have NAs. R has NAs for logicals, has NAs for floating point data, for integers, for character data, has NAs for all its basic types, which is something. Array operations then. So why do we do array? We use arrays because we can operate on them, right? And a lot of these things are really trivial and are element-wise. For instance, if two arrays have the same shape, like here, we can just do an arithmetic operator. We can add them, and we can element-wise addition. So a lot of these things are element-wise. Here, the product is also element-wise. There is also the matrix product, which is a completely different thing. Anyone ever been in linear algebra? Do you have a question? No. Anyone ever in linear algebra knows that matrix products are inner products of columns of the left-hand element and rows of the left-hand and columns of the right-hand side, and so to get a different shape and so on. There's a different expression for that, so we have all these expressions in R where arrays can be used, can be put in, as long as they fit in size and so on. If they don't fit in size, you get either an error message or it will replicate things. So we can also, add, for instance, say a matrix plus 1, and then 1 is added to every element. So it first creates a matrix with 1s and then adds the 2. Basically, that's what happens. So we can have, here is a number subtracted, here and dividing by a number. So every element is divided by is a square of each element-wise. Here is a modulus of each element. This is what ChatGPT did for me. All these examples, I love it. This is what I brought in. This is a logical array. So we can do logical operations, and every element results in a true or false of these things. And you can do subsetting with logical operations. So you get the elements for which a certain condition is true. You can compute the mean, which is then operates just all the numbers. It computes the mean for, or the standard deviation, and so on. Range. We can get the dimensions. As we saw, this is the basic property, right? The dimensions of the array. The length of the underlying factor, the number of elements, and there are different printing methods. We can tabularize them. And here is more interesting thing. Here come array operations with apply, and array operations with apply do the operation to particular subarrays, right? So array apply a1 comma mean means that we apply the function mean to each row, to the sort of for each element of the first dimension. And here we do that for each element of the second dimension, right? So we can also do it for combinations of dimensions. Here for the third dimensions, we can do it for each row and column. So do the mean over all these, all these sort of chunks that I had this morning in my nice hand-drawn slides. All these sort of the vertical chunks you iterate over 2 dimensions and apply the mean of the remaining dimension. So this is a very powerful concept. You have lots of numbers, and you basically want to operate on certain things. Yeah, you have like your spatial slices, right? And you want to compute the area that is flooded. So you have a condition, blah, 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 this number is larger than that, it's flooded, and you compute all the cells, and you get true and falses, and you sum them, they're ones and zeros, and you get the number of cells with flooded, and do that for every time step, right? So that is the operation that you do there typically. So so those are this is kind of what we call functional programming, that we have an iterator, so to speak, and a function, and the function is sort of iterated in some fashion over a data structure, right? So the function mean is an argument in another function. So that is a very powerful concept. The same thing, and then I don't think there's row means, col means, slice means things, and then we have the subsetting, which we already looked a little bit at. Here, subsetting with commas and no arguments means that means that this is the first row, and all the columns and all the layers, so to speak, right? First row across all slices. Yeah, so these kind of slice the matrix in different ways. Right, that is slicing. So that is something we can also do with NumPy. I'm sure that also works. It's always long. We do the same thing here, so we don't do. So we have the dimension 2, 3, 4. So we have the other sort of setting here, but we can do element-wise and element-wise additions, products, and so on. And sort of work our way through that, do logical matrices, logical arrays. And here we get these things like the size or the shape of these arrays. And we can also do the np.apply along axis, right? Which is the apply, and in R, we can do the np.mean, which is the function, then the dimension over which we iterate, and then the array over which we iterate. So this is exactly the other way around, where you first give the function and then the dimensions, and then the area for which you do this. This is np.apply along axis, means basically that this function exists in the NumPy namespace, right? So it's a function call with a function as an argument. So it's exactly the same thing. Gives you a subarray where the mean is done over a particular dimension. And then we have all the slices. That works a little bit differently. As you can see, you can, in Python, you have this colon when you want to say all the elements off. You say colon and then comma, colon, comma, 0. That's the first slice, right? So so we get we have to put these columns there to indicate that we want to have all elements. Yeah, that's it. So that is basically linear algebra, right? So there is nothing new, except that now we're going to look at how this works out for raster and vector data cubes in R and Python. And as I said, linear algebra is a big thing. So everything is there: matrix vector multiplication, matrix multiplication, determinants, inverses, eigenvalues, singular value decompositions. We heard a few of these things this morning. They are there, and they are basically the ingredients of everything: statistical regression, machine learning, deep learning, and so is all sort of built on these stones, right? The convoluted neural network is a convoluted logistic regression model. Logistic regression model is a generalized linear model. Is sort of an iterative regression model. Regression models are based on normal equations, and normal equations are just the solutions of a set of linear equations, right? And the solution of a set of linear equations is a matrix, is a linear algebra operation, right? So the whole thing, the whole stack of all the analysis, and the time that's spent in linear in fitting models is almost always, if things go well, is spent in your linear algebra, right? If you did it wrong, it's spent somewhere else. It's, for instance, in the reading and the writing of the data. Then you have a problem, right? Then you can, because you can optimize that out. You can rarely really optimize out the linear algebra things. You can optimize that by using libraries that use multiple cores or something like that. right? Try to make it faster with the hardware that you have, but you cannot get rid of it, so to speak, right? If you need to do an singular value decomposition of a massive matrix, then that's just a lot of work. Then it takes a long time, right? That's just how life is. And maybe you can, maybe you can optimize it by only looking for the first 20 singular values, which is truncated singular value, which is of course quicker and so on, harder. That could be a way. So that's there. So that is basically where your computation spend when things are done well, right? Now we look at raster data cubes and vector data cubes. Are there any questions so far? Is there anyone? Are some people also trying to run these scripts in while I'm talking? So I'm talking a lot. I know it's hard to do two things at the same time, but so I try not to. I just look at the result. You can run it. I just essentially I ran it just here, but in batch. And you can, in principle, you know, as here you can do it chunk-wise, right? You can say, you know, where am I? Here in this section. Oh, here's the R section. I can run this cell, and then I run this cell, and I get the output here. And I can, of course, here run the, you know, run the Python cell, and it runs here. Oh, it's just not nice. Well, it ran. I messed up I have to restart my. Oh, I don't know. Yeah, why not do this? Yeah, do it. Just get rid of it. Oh, doesn't. Well, it's, you know, it's all experimental software, so this is what a good thing about it. So so raster and vector data cubes basically are array structures where array dimensions are associated with spatial coordinates and typically also with temporal coordinates, right? So otherwise we could say, well, we just have a raster map and we do it with graphs and all set, right? So so the idea of data cubes comes really from the need for more than 2 dimensions, maybe 3, 4, 5 dimensions, and so on. And so how they are handled, and we can see how this is handled in R. So the data cube is basically a metaphor for an array, and of course cube you think 3-dimensional, but it is about multi-dimensional. It's about any dimensional. So you could also speak about hypercubes in that sense, right? We had hyperspectral this morning. Hyper is a nice connotation, like, but we just say, we leave it out. We say data cubes is sort of difficult enough. So we have one or more spatial dimensions, and then we call them vector. There is this difficulty. I will get back to that when we go in the second step to vector data cubes. That vector is here as in the connotations of raster and vector data. Yeah, so for many of you, this is obvious. We have raster data, we have vector data. If you think GIS, so there's like raster grids, vector, point lines, polygons, and not in the sense of the vector that we had here, right? It said here is a vector. This V is a vector, right? And I say here as vector and so on. This is the, you know, the linear algebra vector, which is a different thing. Vector. We think of vector geometries. So raster geometry data cubes, vector geometry data cubes. Maybe we should have used that as to make it more, to make it less ambiguous for some people. This is confusing. So I'm using here package stars because well, it's there and it does certain things well. A lot of people use Terra, and we saw there is quite some Terra tutorials this week. Terra is a fantastic package written by a highly respected colleague of mine, also somebody from the Netherlands, but living in I think Robert lives in Davis in California. And they are different. And with the package stars, I really try to STAR stands for spatial and temporal arrays. And I try to stay as close as possible to the R arrays. Yeah, so whenever something is read, whenever you read a raster file, a raster layer, it's read into an R matrix. Yeah, so, and then of course, then it's just a matrix, right? So you don't know where is what and so on. So then it needs to keep metadata on what are the rows, what are the coordinates of the rows, and what are the coordinates of the columns, that kind of information. What's the coordinate reference system? These kind of things you need to do on top of that, right? You cannot just, you can, of course, it is what mathematicians would do, is just sort of throw everything in the matrix and forget about the rest, right? And then write a script that gives you the map in the end, but where you just pray that everything went well, right? But there was no checking or anything of coordinate reference systems, or just because but mathematicians doesn't make these kind of mistakes. I have said very nasty things about mathematicians at conferences. I shouldn't do that. The package star, so package star tries to stay very close to arrays, and also tries to sort of give you the full power of arrays, so arbitrary dimensioned arrays. So it can deal with 8-dimensional spatial data cubes. The package Terra is written with a very somewhat different mindset. It's tightly linked to GDAL. It has a GDAL model. It says I can have a raster file or a set of bands, but it's not very much. It won't. So if it has bands, of course, it has a third dimension, and you could even put time labels on bands, but it stops there. In the sense you cannot have like multi-band, multispectral information that varies over time, because that would be a 4-dimensional data cube. It doesn't deal with higher than 3 dimensions. I don't think it does. I don't think it does that, or does it well. Yeah, so STARS is more like set up with that idea. Also, STARS has much stronger integration with SF, which is not a surprise because it's the same author. And also does vector data cubes, which are basically arrays where an array dimension is associated with a set of points, lines, or polygons, instead of like a longitude or a latitude and a single spatial dimension. So it's associated with a set, which is a nice thing, as we will see a little bit later. So here is a very simple example where I create an array from scratch the way I did it before. So I'm using array here and creating a 10 by 10 by 5 array with some random noise added to it. And I say it has dimensions 10, 5, and 5. You can also see that I'm naming the dimensions here. You can do that. And then I see it's converted to a stars object. Let's see what comes out. It says then this is a stars object with 3 dimensions and 1 attribute. So the attribute is this A attribute, right? It's here, and you see a summary of A, a numeric summary in 5 numbers, 6 numbers. And we see here a little dimension table, and the dimension table is pretty empty. It just says, well, X ranges from 1 to 10, Y from 1 to 10, and time from 1 to 5, because it doesn't know anything else, right? I didn't feed it with anything, but I could sort of say a little bit more about what's going on, what the values that are associated with X and Y and time are, and then I get a little bit more information. I can also set the coordinate reference system to something that is well understood, the coordinate CRS84, which is the WGS 84, but then with an expression that longitude comes first and latitude second, which WGS 84 doesn't do. Or EPSG 4326 does not do that. It's sort of the wrong one. It's the wrong specification. So I get I enrich basically the same object. I enrich it now with information about the offset and the delta, which is basically the upper left corner of my raster and the cell size, and the upper left corner in terms of Y and the cell size. So it's a regular grid because I just gave it regular numbers with coordinates. And it has now a reference system. As you can see here, it recognizes X and Y as the X and Y coordinate of spatial dimensions, which is useful if I'm going to plot them. And it has now a time axis, right? It says the offset of my time is this first date, and it has a time step of 1 day. So it uses offset and delta, meaning it recognizes that these dimensions have regular values. Yes, that is an interesting thing if you come from the modeling world, if you're used to netcdfs or to ZAR files, because they don't do that. They don't have that. They say, well, we have just the coordinate longitude, and here are the numbers. Here are the coordinates of my longitudes. And these longitudes may be regular, or typically they're almost regular, right? Because if you compute longitudes along a sequence with a certain, well, for instance, with a step size of 1/3 of a degree, right? You get these floating point numbers. So you get steps that are, that are almost exactly 1/3 degree. It's just 1/3 degree you cannot represent in a computer with a floating point number. So you get this, you typically have regular X and Y dimensions, but by listing all the coordinates of all the dimension values in real cases, you get to this issue of, they're almost regular. When shall I decide these are regular? When shall I decide these are not regular? Well, and of course, if you always keep the numbers, then you could be fine. But if you do then a reprojection, all the numbers are recomputed and so on. Anyway, that's an interesting conflict. So this is what the modeling community settled on doing. It's in the CF convention, so all climate forecasts should do this. And this is basically defining the start, so the corner of a raster, and then the cell size is another way of doing it. That is basically the GDAL way of doing that the geospatial sort of GIS and geospatial and Earth observation communities settled on. Yeah, so if you read a GeoTIFF, then it does not have the coordinate numbers of the rows and the columns. No, it has the coordinates of the top left corner and the cell size. And of course, the number of rows and columns, right? The size, yeah? So the coordinates themselves are implicit. It can be computed from, and there's a function that does that, right? So that's an interesting different thing there. In the whole, if you follow on GitHub, if you follow the whole discussions about GeoZAR, so that is where the geospatial community interacts with the ZAR community and says, well, we can use ZAR for geospatial data. How do we do this? There are lots of discussions about, these. In GDAL, it's called the geotransform. Yeah, the 6 numbers that basically define the raster. You would say there are 4 numbers. Yes, you are right. However, this up. However, we also have what is this? Something went wrong here. So we also have these kind of grids which are rotated. Yeah, or we have the shared grid. So if you use 6 numbers, you can represent these first 3. Yeah, and that is what GDAL does. Although, of course, in almost all of the use cases, you are looking at a regular grid where 2 of the 6 numbers are 0, the rotation numbers, rotation and shear numbers. So that is different models of defining a raster. So here's the plot of the first, basically of the whole data cube, where you see that it goes from left to right. So the dates are plotted on top, and then you see it goes up, right? Because these numbers goes up, and I added a little bit of random noise to make the image a little bit more exciting. In Python, you do a similar thing. You do this with Xarray. Now, Xarray is the package that builds on NumPy, and that is meant for labeled arrays. So NumPy is basically matrix linear algebra. You're not going to label, you're not going to say what individual rows and columns are, because we are doing mathematics and we know, right? So we're not, but Xarray says, well, sometimes it's very convenient for every row if we come to know what it is. For instance, if you have 2 spatial arrays, you want to know the coordinates because you want to sort of combine it. You want to look up a certain place, not by the row and a column, but by the location of a certain place on the Earth, where you know the coordinates and you don't know the row and the column. So you can do these things. So here is an Xarray created, and we're basically doing that in a similar way with a range of 2 dates, and here a range of numbers and so on. And we get this array here. So we ask for the array, and we see the array printed like this. So this is like a NumPy array. And this is nice that it has this this thing that you can here look at the coordinates. It says I have 4 coordinates. Interestingly, time I can see y was these numbers and x. So you can see that the order is reversed, right? It's time yx. That is sort of how X-array NumPy do this. And then you see this coordinate spatial ref, right? I did set somewhere. I set the right CRS. So I wrote this 432 EPSG 4326 CRS to this thing. And if I print this CRS, as you'd see here, then it says EPSG colon 4326, which is the official symbol, right, for WGS84 in the EPSG catalog, with the ambiguous that it specifies that latitudes come before longitudes instead of after longitudes, which is what everyone does. So it's a thing to get rid of, but nevertheless, it says it has it here, and then I print the array here, and it says spatial ref in 640 for some reason. I don't know why this is. There's these interactions with the Rio thing, which is the GDAL kind of raster IO thing. Rio X-array, the raster IO extension to X-array, which basically pulls in some kind of information from GDAL and Proj, I think. So I can then plot the thing here. I only managed to plot with a single time slice. So this is the first time slice, and it gives me this plot. Again, with spatial ref is 0. I don't know why. Maybe the 0 stands for EPSG 4326. Does it? Yes? Yeah? This one? This one? Oh, look at that. Oh, thank you. Good. There it is. There it is. The full information about. Okay, it's there. Fantastic. So this is the. So we see all the elements of the geographic coordinate reference system. This is the well-known text representation of this thing, and these are the parameters. Okay, so we can work with that. Thanks. So let's do something with some real data. So here is a simple example data set, a small piece of a Landsat 7 image from long time ago. It's from an area in the coast of Brazil. And we can see here, if we read this with stars, this read stars, reads this thing. This is just to find the file on my files. It's in the package structure, and I just don't want to bother where it is, but it knows where to find it. And it reads this UTIF file, and you can see that it has like 350 by 350, and then 6 bands. And it's somewhere, it has funny numbers. It has cell size of 28.5 and some offsets that are understood in a local coordinate system, which is some kind of UTM zone 25 south. Yeah, that is used for this data set. And you can see that the numbers range from 0 to 255. If I plot this thing, this is the default plot that stars does. You can see that we get this funny legend that the numbers from 100 to 250 are all the same light gray color, that we have some kind of histogram stretching over these 6 bands. Yeah, that we see. It's kind of what you do with photography with high dynamic range. Yeah, that you basically blow up the shades, that it's not all dark, and so that you see some things. And for imagery, it's quite useful. We saw on this in the third keynote this morning, log scales, right, for variables, because they range, because then you see something going on. If you wouldn't do that, you would just only see dark values or light values. So this is the plot of this is I tried to plot the whole object here, the whole object, and it gave me a histogram of the values. Yeah, you can do that. I was able to plot the first band and plot it, and I get this one, which indeed shows a very dark image, right? So it would have been nice if there was more stretching of the colors, right? But you can probably do that by specifying ways of choosing your color breaks, right? Color breaks are now linearly, equal breaks are now linearly distributed over the data range, and if the data is 0 to 100 range, then your plot gets very boring, and so that happens. I'm not trying to criticize. I'm just exposing how little I know about Python. Yes. Vector data cubes then. Finally, and we're also over time, right? I can see now. No. I had until 3 o'clock. Okay, so we have a lot of time for questions then. So vector data cubes then finally are similarly array structures, arrays, arbitrary dimensioned arrays, where one or more of the dimensions are associated with a set of feature geometries. Yes, feature from simple features. So a set of vector geometries, if you want, points, lines, polygons. And simple features then has points, multi-points, line string, multi-line string, polygon, multi-line string, multi-polygon, and if you must, geometry collection, but you better not do that. And they are basically stored and analyzed, for instance, to have time series for features. So this is a very common case where you have well, think of socioeconomic data where you have administrative regions or countries, and you have yearly numbers for population numbers, for GDP, for all kind of indicators, financial indicators, economic indicators, and what. You have time series of them, right? So where are you gonna put them? So how are you gonna put that in a table, right? So you have several variables, you have several countries, and you have a number of time steps, like 20 years. Yeah, those three things. So there's a lot of ways you can put that in a table. Yeah, one way would be country, year, variable, value, right? And have all the values in one vector. Like this is what I call a long table. So that's the longest table that you can make from that data set, right? The other would, for instance, have countries, rows, and then as column, variable A year 1, variable A year 2, variable A year 3. So you're basically using the variable, and you get variable B year 1, variable B year 2. You get all the columns, right? Where the column names have to be combinations of years and variable, which is a mess. Yeah. So this is. So anyway, it's not like as if you can do all these things, and actually people do all these things with tables all the time, and it's very messy. It's very messy. Yeah. It's just, and the code is just like, it's terrible. But that is, of course, for people whose life of data analysis is restricted to tables, two-dimensional tables. So if your life is restricted to tables, and you say, well, it's hard to read, but it works. It works in the end, and indeed it works. But the nicer thing is to do things with arrays, even if there are two-dimensional things, because if you have like only one variable and you spread your time over rows, and you have your countries sort of as the records in the vertical space, and you want to do a time series analysis, you have to operate on individual rows, right? Which is very unnice to do, to iterate over rows and pick all the elements from a row, right? It is, I mean, if you would do it for a larger data set, you would figure out that it's not flying. Anyway, we have here an example where we say, okay, I'm going to read here this. This is an interesting data set. This is an NetCDF. Yes, I try to find something terrible from the modeling world. Oh, not something terrible, but something good. This is sea surface temperature, a global grid from where the sea surface temperature was sort of served. And as an example, this is a data set taken from the, as an example data set, taken from the packet stars, which I, of course, didn't create, but found from somewhere, probably in the US, in the time that they would still serve data on global variables, right, in the good old days. And so it's being read here. This is being read by Read MDIM for some reason. Probably ReadStars didn't like it so much. Read MDIM is similar, but uses a different API from GDAL. GDAL has extended to actually be a good tool for reading and writing multidimensional arrays, such as netcdfs and ZARs as a main tool, but also HDF or HDF5 files and so on. And sometimes that works better, and here it might work better. Let me see what happens. What I did here was reading this thing and then sampling some points. So I computed the bounding box, which is the spatial bounding box of this object, which has global extent, and I said sample 20 points randomly out of that, and then extract from this data set with 20 time steps, with 24 time steps of monthly values over 2 years from sea surface temperature, extract the values at these points. Yeah, so this is a very common operation. You download, somebody has global sea surface temperature, you're interested in the sea surface temperature in the area where you're looking at. So you want to have that, so you do a point sampling, point extraction. And then you basically get a sub-array that has the same number, the same time dimensions. It just does not no longer have this grid. I can do this sort of. Let me just show you what this gives, because it's not shown. So you can see here that this is the file is now being read, and you can see here this is the TOS, temperature of surface, I think it stands for, and you can see that it has a unit of measurement. Yeah, so this is the nice thing about that CDF, as mentioned this morning, ZARs, that typically people follow CF conventions and give numbers, also tell what unit of measurement it is. Yeah, this is a fantastic thing that it's really embarrassing that the rest of the world does not always do this. Yeah, because if you have your units and you propagate your units properly, you can find gross errors, right? Where somebody adds temperature to altitude or something like that, right? If you try to do that, you have units and you have software that tracks units, it says, no, you can't do that because kelvins and meters cannot be added. Yeah, you can multiply them, you cannot add them. And that's something that if your world is cloud optimized geotiffs, it's not there, right? It's not there. No, it's not there. So you have all your production numbers, right, which have very complicated numbers that would be nice to actually have, yeah, in your when you read these files. So there's the units, and there are the numbers that we now also can recognize as Kelvin numbers, and there's of course a lot of NAs because it is sea surface temperature. All the land surface has NA. And you see that this is a 180 by 170 degrees, so 180 by 170. So it's 2 degrees longitude steps and 1 degree latitude steps. So that's 90 plus 90. Yeah, so it cuts off somewhere. Maybe Antarctica is cut off, but we can plot it. So here it is. Yeah, so it stops somewhere. It seems to go into plus 90. Yeah, it starts at minus 80. So minus 80 is the most southern point because I guess below, more southern than minus 90, maybe there is no sea. I guess that will be the reason. So that makes sense. So you can see that this is a 2 degree by 1 degree grid that it doesn't have a coordinate reference and couldn't find that. That our time axis is interesting, starts here in middle of the month, has a delta of 30 days, and has a reference system called T360. That means that it's a time, some kind of a time axis where a year has 360 days. This is because it's convenient, right? We can do that. Why not? If we do, if we model processes in the Earth, why admit that time is complicated? Why not make things simple? So that's good. It's good that it's recognized, and that happens in some of these files. It's messy if you have to convert it to the times as we understand them. But anyway, we can handle that, and so we can extract these things. And what we then get is the time series for every point, right? And so we get these points. So we get basically a dimension now that is called geometry that has these 20 points. So for these 20 points, we have, for each point, we have 25 time steps. These are the time steps. This is the offset is the first time. This is the time step. And here we have the geometries, yeah, not all of them written out. And this is it. Right? And then we see the Kelvin numbers for the sea surface temperature at these points, and we have a number of NAs because of, so we have 24 times. So this is 4 points that happen to fall on land where we don't have sea surface temperature. So they become NA. And then we can do, for instance, we can look at them, but it's time series per point. So how do we visualize that? There's all kind of ways you can do it. The simple way is to convert it into just an XDS object, which is a collection of time series. So we get here the 16 time series, 16 points, 16 time series over the period, over the 2 years in an XDS plot. So we can look. We see this by sort of the yearly curve on the northern. Oh, hang on. This is the northern hemisphere. These are the curves on the southern hemisphere. Yeah, so that makes sense. Similarly, in Python, you can do this with GeoPandas, X-array, Ryo X-array, and Shapely. Shapely is just to create a points. I have here I had to open the data set here. So that data set means that there's multiple arrays in this data set, and then I can get a single array by indexing using the name of this particular array. So this takes the temperature of surface out of this data set, and then I get these coordinates, longitude, latitude, and time for R for the array. So that is again, so you see here the numbers of the coordinates, right? So let me just click on this. Well, that doesn't help much, but oh, here they are. So here you see actually the numbers of the arrays. Yeah, so that is something that R wouldn't do. So it's a netcdf file. So they're in the netcdf file, and in the previous section here, you can see that they were reduced to something that is, you could see it here, to something that's regular, right? It says, I have an offset, I have a delta, I have constant intervals. Yeah, so that the numbers are thrown away, basically. Here, but I can recompute them. And here they are put in the, and it's also quite often that these dimensions are, that they are actually irregular, or that they are slightly regular, almost regular. Yeah, that you have like a half a cell at the left side of your grid and half a cell on the right hand of the grid, and these kind of things. Also of interest is obviously that we have now longitude coordinates ranging from 1 to 360, where, when some of you might be more familiar with the convention of, saying that the world spans from minus 180 to plus 180, which is a different way, right? A different starting point, and this basically starts at the Greenwich meridian and goes round. The other way would start at the anti-meridian and then go round and end the anti-meridian. So those are two ways. That is always like a messy way to go from one to the other. Here you see the latitude values, right, which are nicely regular, right? Sort of, you can see that. And then we have the time values. Over here it also uses, it says, I had to load this package CF time. So it says date time 360 day. Yeah, so this is the a construction of a variable that acknowledges that this is a date time in a 360 day calendar system, right? And it says the year, the month, the day of month, right? It's always the 16th of the month, and these months are clearly 30 days long, whatever the month is, right? For reasons of not wanting to admit that time is complicated. It's understandable. Right, so what we then do is we find a bounding box and we create a number of random points here. So this is a different set of random points because we of course have a different random number generator in Python than in R, so it's not exactly the same. We set the coordinate reference system here, and we can then with r.cell we can sort of take out the values of the array at the longitudes and latitudes of the geodata frame, right? And so the method we do that is the nearest. That means that we basically we look at the point in pixel, right? So if pixels are considered as points, the nearest point is basically the pixel you're in. If these pixels have a regular rectangular shape. So we find then the X array, and I don't know exactly what this means. There is these things with, there are still longitude and latitude, but there's also a coordinate that says points, which are basically the index of the points, the 20 points that I have. And I think long and lot are the corresponding longitude and latitude coordinates of these points, right? So the array is 25 by 20, yeah, 25 times 20 points. But there are two additional arrays or coordinates that have essentially the values for the values for the points. And interestingly, these are the centers. Yeah, so these are not the randomly generated, because random uniform generated points are uniformly spread in my bounding box, and these are latitudes of the original raster. So long and lot is the other one. Long and lot, right? So we get something that is the same data structure at 24 by 20, which has points, has an index, and has two additional coordinates for latitudes and longitudes, and this then gives that essentially that vector data cube, right? I was not able to print that as a time series because of my limited knowledge of Python, but that would be just a matter of time to squeeze that out of the LLM. There is another package. So this all works with Xarray and works fine. There is of course case, the additional case where you would, for instance, want to compute an average over a region, right? If you want the average sea surface temperature, for instance, over the Mediterranean and the North Sea, right? You could do that. That would be another operation, and I think that is something that is done or that's made available in the XVAC package. So you would then get sort of, for every polygon, you would get some kind of function of the pixels that are underneath this polygon, and that is not possible in this setting, in the sense that you cannot put a set of polygons in a long and a lat variable, right? So you need then, for points, you need to, instead of a set of indexes, you need to have a set of geometries. And I think for that use case, the package XVAC was developed. Actually, that started when Martin Fleischmann and I were discussing vector data cubes at the waiting for the trains when we came back from a meeting at ESA. over a beer, obviously. And he started this thing, and that kind of does that. And I'm now doing the same thing essentially with this array, except that I'm using the HVAC function, the exact function extract points that says the x score is long and lat. Create an object called E, and E then an X-array object that has the geometries here, right? As the second coordinate. It's funny enough that the second coordinate doesn't have a name, but so time is obvious, but the second coordinate has the geometries really as an array of simple feature geometries, right? So you could also have an array of polygons there, or an array of lines, if you are interested in, the average sea surface temperature along a certain shipping route or something like that, for whatever reason. Then you could do that, right? You could say, I'm gonna read this raster file along this line and compute the mean, and so glue that on this line or on this point or on this polygon. So that is a Python package for Rust for vector data cubes that extends that functionality of just extracting things at points, but extends it to also, well, first of all, it handles the geometries in the proper way as that you would handle geometries. Second of all, it can deal with non-point geometries, right? And can handle lines and line strings, and can do these things like I think they make now an interface also with exact extract, which is this software that does very efficient extraction of polygon values over rasters, where it also deals with raster cells that are partially covered. It will sort of weigh them in for the extent that they overlap, and so these kind of things. So that is as far as I got in this as far as I got in this workshop. And there are more examples here in this book which I pointed you to. That is the spatial data science book, but then the Python version, right, which has Python here. And in the chapter on the package stars, we now, with help of my colleague Mohammed Al-Sabeda, we have now most of our sections translated in Python too, so we can basically go through these things and sort of see what's going on. There is the subsetting that mentioned there. There's the cropping of rasters to subrasters with a certain polygon. There is the cropping, redimensioning of things, transposing. There is the splitting of things into where you split an array dimension into subarrays of lower dimensionality, like all the layers into bands with names. These kind of things are very useful in analysis, but also extracting point samples and aggregation is handled there, and has examples that use IfGI and that use zonal stats. Yeah, the IfGI zonal stats is basically for a particular polygon you want to have, for instance, the maximum value over that polygon. It also has an example nicely with which uses these data structures in the prediction setting. So here is a data set, 20 points. It's a little bit hard to read, but you see numbers which are sample numbers that are taken on land if they are yellow, and that are taken on sea if they are red. So there are 5 points at the sea and the other ones at land. And we try to do a linear discriminant analysis with LDA here. Oops, LDA, don't go there, don't go away. Stop. How do I stop this? Okay, with LDA, linear discriminant analysis, and then predict this and puts that in a map, right? Predicts the class, land or water, which is a fairly trivial problem here. But nicely, I actually we managed to do the same thing with Python. You can see that here with sklearn, scikit-learn, I think, discriminant analysis, import linear discriminant analysis, so it does the same thing. And here we have to do the same. So this took me 2 hours to find this one. We have to label things. We label everything as land, and then there's these 5 points that we label as water, except that, of course, the index has to be one lower, has to be one lower than the index in an R array. So Copilot suggested that it would be proper Python, but forgot that indexes are zero-based in Python. It took me 2 hours to find that one. But an interesting experience. And so Python, and look at this here, ta-da, this map, and also these little structures, we really find this sort of pretty much exact thing back from the linear discriminant analysis in Python. So that gives some comfort that both implementations are either correct or contain the same errors. The interesting thing, of course, would be now doing these kind of things to have, a little section beneath here that actually compares these two maps and computes the number of cells where they do not correspond. That should be 0 or very small. And that is work in progress. Yeah. Once we are here, we can do these things, but it's still figuring out this a little bit. So this is what so you can look at it if you have any suggestions to improve the R code or the Python code in particular, or have other ways or better ways or sections where you think, hey, I can do this, then please feel free to contribute. This whole book is in GitHub. There are many contributors, and you will be mentioned and gratefully be thanked in the introduction of the new edition to appear sometime in the next years.